Okay, I thought I'd all right, rolls. When something is rolling along, okay, when if you've ever been on a slick day and you can't get traction, you don't go forward. In other words, when you put your foot down, when you put your that static frictional force is what is pushing you forward. Same thing in a car. That's why if you actually watch those dragster videos, you saw them burning the rubber first. That's so that they could get traction because they want to get maximum traction with the road so that they get the maximum them forward. Static friction means it's not moving. Whenever a wheel turns, when it's at the very bottom, when it's at the very, very bottom, uh, um, that's touching the road, the velocity of that wheel is zero at that point, and it's going twice as fast up at the top. Just go with it. All right. Anyway, and it's that static friction on the four tires. Basically, in the dragster, it's on the two back tires that's pushing it forward. That's what I later. But being a physics geek professor, it is that's pushing. It's not the engine does this. The engine provides the torque friction on the in the ground. Still very simplistic. I'm sure an automotive engineer or a mechanic would say, well, yeah, but that was correct. All right, so listen, where did we stop? Oh, question number 16. I did a quick calculation to determine that the dragster went about 250 meters in that burst of speed from 0 to 265 miles an hour, or 114 meters per second for those of you who computed that later. What was the work done by the static frictional force to push the dragster that far? Well, we know the work done. So on problem 16, we got this thing happening. Problem 16, we know that the work is equal to the force that you computed before, mass times the acceleration, times, and we're assuming, I'm making a huge assumption here, that it is accelerating at a constant rate the entire time, is equal to the force which you computed times the distance which I gave you. Okay, so now we go on to problem 17. Guess what we're going to do? I'll bet $1 to a donut we're going to compute the power. Okay, so on 17 you compute the power. What was the time? 4.38 seconds. What was the work done? That's from up here. So you take this force times distance divided by 4.38. You've got the power. You got the power. And then I want you to convert it to horsepower. And when you convert it to horsepower, you're going to take that thing in watts and multiply by 0.00134. Now, here's the cool thing. You're going to come up with an answer, I'm going to tell you right now, between 1,500 horsepower and 2,000 horsepower. That's not the right answer, but it's going to be in there. All right. Now, here's what made me kind of feel good. I went to Top Fuel Horsepower just to find out what it was, what it actually was, and here's what I found: 11,000. Whoa! But wait, back in the 70s, before they had all this fancy gear and accelerometer equipment and all that, they'd computed it around 2000. So I was really proud of it because I was making huge assumptions. I was making huge assumptions that I'm going to put my mug back on here at the risk of losing this whole thing. Um, I made this huge assumption that well, I imagine for a very short amount of time, there's a huge acceleration for a very short amount of time that does an incredible amount of work for a shorter distance. So you get that force times that huge acceleration divided by a short amount of time. That's where you get the 11th, and then then the acceleration as it goes along dissipates until it probably just going to constant velocity. All right. At that point, it's not accelerating anymore, and that might have been and that's what prompted. I took and came up with our answer. Have fun with this. Hopefully, it wasn't too crazy, and you learned something about a sport. Maybe a lot of you, we saw how we could bridge the science with it, and but for me. So out here, have a great. If you're doing this on next Friday, I hope you have a safe Labor Day weekend, and I will see you on probably Wednesday.